In this section, we're going to talk about quadratic functions as another example of functions. So let's start with the definition. A function f of x is a quadratic function if it can be written as f of x equals ax squared plus bx plus c, with a not being 0. If a equals 0, it's just a linear function. So let's talk about a couple things regarding quadratic functions. The first is the graph and some of the properties that it has, and then that'll lead us to talking about parabolas and some of their standard features. And then the most important part in my mind is then the applications of the quadratic function. So let's start with graphing. If a quadratic function, like the one given down here, is given in the form ax squared plus bx plus c, then it's a difficult function to graph by hand, unless we complete the square. By completing the square, we can write this in a more familiar form. So let's see how that's done. So to complete the square, we're going to factor out the leading coefficient, the leading 2, from every single term. This is slightly different than what's done in the book, but I think this is an easier method. So every term, we're going to factor out a 2. Now for the first two terms, that's not too bad, because we have x squared, we have 2x, and we divide by 2. The last term isn't an even number, so when we divide by 2, it's actually a little bit forced. So we'll actually have to rewrite that as being minus 1/2. That is, when we divide 1 by 2, we're left with a 1 over 2. And you can check, if you distribute the 2 back through each of the three terms, we have 2x squared plus 4x minus 1. Now we're going to go through that completing the square process that we talked about in finding the equation of a circle. The trick here, though, is that we don't have an equation, we have a function. So we can't add the same thing to both sides as we did before. So instead, here's what we're going to do. We're going to start off the same process. We're going to look at the number in front of the x squared and take half of it. So half of the number in front of the x. So that gives us 1. And we're going to square that, and we're going to add it in here. So this would be 2 times the quantity x squared plus 2x plus 1. And because we just added 1, we're going to subtract 1 so that the resulting process doesn't change our function. So this is still the same function. All we've done is creatively added 0. And now by design, we can factor the first three terms as being a perfect square. So x squared plus 2x plus 1 becomes x plus 1 quantity squared. And then the last two terms get grouped together. So negative 1 minus 1/2 is negative 3/2. Think of negative 1 as being negative 2 over 2 minus 1 over 2, you get negative 3 over 2. And now the last step of the process is distribute this 2 to each one of these two terms, and we get our new function, our new form of the function, we should say, is being 2 times the quantity x plus 1 squared, and then minus 2 times 3 divided by 2. 2's cancel. You get minus 3. So this expression on the right hand side is exactly the same as the one over here. It's just been written in form where we have explicitly a term being squared, multiplied by a number, subtracted from something else, or a number being subtracted from it, which is exactly what we want to see if we're going to try to graph this. Now that the quadratic function has been written in this new form, now it looks like a problem from the previous section. We can graph this by starting off with the graph of x squared, moving 1 to the left because that 1 is going to directly affect the x values, and because it's a plus 1, it's going to move the graph to the left by 1. It's going to stretch vertically by a factor of 2, and then we're going to go down 3. So if we put that process into action, negative 2 squared is 4. There's that first point. Negative 1 squared is 1, 0 squared is 0, 2 squared is 4. So there's our x squared graph. We're going to move that to the left by 1. Every term gets moved over by 1. We're going to stretch that vertically by 2. So every y value gets multiplied by 2. So this y-intercept at 0, 1 now becomes 0, 2. So our parabola gets a little thinner looking. And then we're going to move this graph down 3. 1, 2, 3. So now we have a thin parabola that turns around right here. And what's special about this point is what we call the vertex, the turnaround point. Vertex or turning point. And it's a point on our graph that has, so it'll have some coordinates to it. So the x-coordinate is -1, the y-coordinate is 3. And what's special about those coordinates is those correspond to our new form of our quadratic equation. That -1 is the number that's being subtracted from x, so x minus the -1 is what x plus 1 is, and then the 3, -3, is the value that's being subtracted from our quadratic. So we can think of this as being this vertex is formed because we took our x squared graph, we moved it over in the x direction by -1, and we moved it down in the y direction by -3. That's why it's located down here, because of our two moves that contributed to that location of our vertex. This allows us to then describe any graph of a quadratic as a parabola in the form of y equals a number, a, times x minus h quantity squared plus k, where a is the same a as ax squared plus bx plus c, and the h and k have that special form of the turning point. That's the location of our vertex. The parabola will open up if a is positive, because that will mean that we didn't have to reflect our graph across the x-axis. All we've done is stretched it vertically by a certain value a, or compressed it vertically by value a. However, if a is negative, that means that we along the way of graphing it had to reflect our graph across the x-axis. That's going to make our parabola open downwards, so it's going to look like this. If a is negative, that's going to open up if a is positive. Let's look at an example of how this standard form of the parabola works. Suppose we're given the coordinates of the vertex and another point that's on the parabola. And let's try to find the equation of the parabola that has that vertex and goes through that y-intercept. So let's start with our equation of a parabola and think about what we're given. So in the equation, h is the x-coordinate of the vertex. Here we know that must be -3. And k is the y-coordinate, in this case 2. So this gives us information about h and k. Plugging that into our equation, that means that we know everything except a. So x minus a -3 squared plus 2. So y equals a times x plus 3 quantity squared plus 2. This a is not the slope of the parabola, because parabolas do not have constant slope. Instead, we find it by using our one point that we know. So the y-intercept means that when x is 0, y is -1. So when x is 0, we can replace x with 0. Y is -1. And we can take that equation and solve for a. Let's do that. So we get -1 equals 3 squared times a, so 9a plus 2. Subtract 2 from both sides. -3 equals 9a, which means that a is -3 divided by 9, or -1/3. So putting this all together, we have our equation. So putting this a value into our original part, we have our equation is y equals -1/3 x plus 3 squared plus 2. And as a check to make sure this makes sense, think of the rough picture. We said that the vertex was at -3, 2, and then there was a y-intercept at 0, -1. So it makes sense, I think, that the parabola should open down, and therefore a is going to be negative. So have a being -1/3 seems to be consistent to what our picture should look like. So let's find the vertex of the parabola by putting it into standard form. So we're going to try to put this in the form of a times x minus h quantity squared plus k. So right now it's already only in the form of ax squared plus bx plus c. The way we're going to do this is exactly the same way as we did when we tried to graph the parabola. That is, we're going to complete the square. So what we did in that earlier example was we factored out the leading coefficient. In this case it's a -1, so we can factor out -1 from all three terms. X squared minus 6x, and then plus 8. And then we completed the square. We talked about what we need to add and then also subtract so that the first three terms are perfectly factorable. So we want these three terms to be perfectly factorable. And our strategy from earlier was to take half the number from the x, so take 1/2 of -6, that's -3, and then square it. So we're going to take -3 squared, so -3 times -3 is 9. We're going to add it and we're going to subtract it. So it doesn't change our values at all. And now, if we continue down and factor those three terms, that should be factored perfectly into our nice square. And then the remaining two terms add up to -1. And now don't forget this last step. This is kind of an important one. To distribute the -1 back through to both these two terms. When we do that, we're left with -1 times x minus 3 squared, and then -1 times -1, so plus 1, which means our vertex is at, so the number being subtracted from x is 3, and the number being added at the end is 1. So our vertex is 3, 1. And for an added bonus, we know that because a is negative, our parabola should open down. So if we wanted to graph that really quick, we can. 1, 2, 3, up 1, opens down. There's our graph.